All right, welcome back. Today we're going to talk about probability generating functions, which is an important discovery by mathematicians to utilize algebra in manipulating probability more um, in a more effective way in this case, right? Now let's look at what are required for your um, exam requirement, right? So let's look at the exam requirement here. Now, at the end of this topic, all the students should be able to understand the main concept of probability generating functions, PGF, and then all of us will be able to construct the probability generating functions, and then lastly, we should be able to discover some of the properties relevance to these uh, probability generating functions. Right now, that's number one. And number two, the students should be able to use the formula for mean and variance or discrete random variable uh, uh, from the perspective of probability generating function. And then hence students will be able to use this formula to calculate the mean and variance of the given probability distributions. Those probability distributions that we are going to focus on would be the uniform probability distribution, a binomial, a geometric, and lastly we're going to look at Poisson distributions. Right. And then the last sections in our syllabus would be students would use the result that the probability generating functions to evaluate the sum of independent random variables. All right, it could be more than two random variables. Okay, now if those random variables are independent, how do we evaluate the sum of these independent random variables using the product of the probability generating functions, which is one of the um, strength of using probability generating functions here, right? So basically we have three subtopics we're going to cover. The first one is the concept, and then some of its properties or probability generating functions. Secondly, we're going to look at how we're going to extend the calculations related to mean and variance. And then lastly, we're going to look at how we're going to evaluate the sum of two or more independent random variables by using the product of probability generating functions, right? So after this, I'm going to show you a few examples, and then let's walk through these examples so that we can appreciate all the properties of probability generating functions and their ability in analyzing probability, right? Stay tuned. All right, so here we are going to I'm going to use one opening question to show you the motivations behind the discovery of or the usage of probability generating function. Right now, let's assume that these are results collected from football competitions, for instance. Right now, the first row represent number of goals um, presented by the team, okay, throughout the game. Right now we can have no goals at all. We can have one, two, three, four, five, or more than five here. Now the number of frequencies, how many times they don't get a goal, that would be 149, and then getting a one goal is 179, and so on and so forth. Right now the chances of getting five goals and above is zero. So is we can say that it's impossible to actually witness the team achieving more than five goals here. Right. Now, the relative frequency is basically the ratio of the frequency to the total. frequency in this case, right? Or you can say that the relative frequency represent the chances or the probability that the team manage to score certain goals during the game, right? Okay, so this is one way how we can represent uh, the result of the outcomes, right? With respect to relative frequency or probability here, right? Now, indirectly, you can say that this is a relative frequency table, or you can say that this is a probability distributions table because it shows all its individual probability with respect to the discrete random variables here, which are 0 until 5 and above, right? So one way to represent probability is in the form of table. Now, is there another way to represent informations related to probability? Yes, we can represent these informations um, algebraically. So how can we represent this? Take for instance, we can actually come up with the functions. Let's call this g, function of g. Okay, so let's call this function of g that has a independent variable of t here. Okay, so the purpose here is for us to generate functions that can be used to represent the relative frequency or probability here. Right. Okay. Now to do that, we can write it down like this. Okay. Yeah. Maybe I'm gonna write it down explicitly. Now t to about 0 because it has a discrete number of 0 here. The second one, third one, and then we have t3, and then we're going to proceed on. Okay, we have one more. Okay, now of course, generally we can write one more to represent this, but since the probability is 0, we can actually ignore that, right? Okay, now this is the functions that we can create to represent each individual probability. Now, where can we get its probability? The probability is the coefficients of these polynomial functions here. Now, the functions that we have created is what we call as the probability generating function. Right? So in short, it's just P G F here. Now, this is a function or this is a polynomial functions that is used to represent the probability informations that we extracted from the table itself, right? Okay. Now, then again, you are asking what is the significance of this, right? Now, one of the significant is since this is probability distributions function here. Therefore, we know that all probability distributions would satisfy this main property. The sum of all probability for all the x here must be equal to 1 then. All right. So how can we actually use the probability generating functions to actually achieve the same result here? Okay, we can do so by, okay, we are going to let t equal to 1 here. So by letting t equal to 1, we can get our g1 function as, all right, so that is 387 and then 0.197 oops 006, that look like 66 there. Okay, and then if you sum up all this probability here, it should actually give you a 1 there. All right. So therefore, we can conclude that one of the usage of this probability generating function is we can use that to obtain the sum of any probability distributions function. So therefore, G1 is exactly the same as the sum of any probability distributions for all value of x that involve in the context itself. Right? So in this case, our x actually range from 0, 1, 2, 3, 4, and 5 here. Right? So now I hope that that is clear. This is um, one of the functions of probability generating functions. We can use algebra now in the form of polynomial functions to generate one of the properties of probability distributions, which is the sum of probability must be equal to a 1 here. So this can be achieved by using the probability generating functions by inputting the value of t equal to 1. All right, so I hope that is clear. Okay. Now next, I'm going to show you another properties that we can or obtain, okay, other than the first property here. Now the second one, I'm going to uh, instead of representing this using this table, we can reorganize the table one more time so that it looks something like this. Okay, so we can reorganize this information here in the form in this format. Right? So you can see that tx ranges from t0 until t5, exactly the same as all these variable here. And then their respective probability given as relative frequency here. Okay. And then therefore, in order to generate the probability generating functions, we can get the sum of the products between the tx and its individual probability here. Okay. Now from here, we notice that, okay, so from here we notice that the probability generating functions can also be written as, okay, you will notice that can also be written as the product, sorry, the sum or product between tx and its respective probability here. For in our case, it is from x equals 0 to 5, but generally we can put an x for all the discrete x value involved in the context itself. Right? And then now this format here looks very similar to um, one of the expected formula. So here I'm going to write down the remark here just to recall the expected value formula is given by this. So for all x value, so you can see that the form of the expected function here looks very similar to the probability generating functions that we have obtained here. Now for this we can rewrite this in the form of expected value here. So we can rewrite this as, so this can be written as ETX. So if you replace the x with tx, now that would give us the probability generating function itself. Therefore, this is the second property of probability generating functions that we can relate it to some of the properties of probability distributions. So one of them is the expected value. And then generally this is the formal definitions for probability generating function. Now this would become the definitions for probability generating function using the expected value formula EX here. Now I hope that is clear at this point. Okay, so there are two properties you need to remember here. So the first one, is highlighted here. The sum of probability must be equal to 1. That can be obtained by inputting a value 1 to the probability generating function here. The second property is, by definition, the probability generating function is given by the expected value of tx there. All right. Now I hope that give you a very brief and general idea the motivations behind the discovery of probability generating functions. Now next, I'm going to show you a few standard types of probability distributions functions where we can build the individual probability generating functions for each one of that standards probability distributions, namely uniform distribution, binomial distribution, geometric distribution, and then lastly, we're going to look at Poisson distribution. All right, stay tuned. All right, just to recap on the all the discrete probability distributions that we have worked with before. Okay, now here we're only interested in discrete probability distributions. They are the first one, uniform distribution. Now, uniform distributions could be used for continuous probability distribution, or it could be used under discrete distribution. For discrete distributions, the general notations is X is uniform distributions with a constant value k, where k could be any real numbers there. So it has a fixed probability or constant or uniform probability throughout the entire um, event. Right? Now the next one would be the most famous distribution, uh, binomial distribution. All right. Okay, so binomial distribution. Now, binomial distributions can be written in the following notations. So x is any discrete random variable that is um, or can be modeled using binomial distributions, having a number of trials n, and then probability of success p there. And then its individual probability calculation is given by this summations formula here, where n are the number of trials, p will be probability of success, and then 1 minus p is the probability of failure here. Right. Now next, we have geometric distributions, can be written as x is a geometric distributions with a parameter p representing probability of success. Now this geometric distribution usually used to represent an event, a number of a failure in the event before a success is being achieved here. Right now, its probability mass function is given as such. So it's 1 minus p raised to the power x minus 1, and then multiply with its probability of success there. And then lastly, we have Poisson distributions. Right now, it can be represented as PO with single parameters here, lambda. Okay, now its probability mass function is given by e negative lambda lambda x over x factorial here. Poisson distributions usually used to study the durations of certain events occurring over a certain period of time. So the lambda here represents the average value, average value over a certain period of unit, over a certain period of unit. So in this case, it could be over a certain period of time, or it could be over a certain period of other units other than time itself. Right, so I hope that this give you a brief idea, just to recap on all the discrete probability distributions that we are going to build the probability generating functions on. So we're going to create each individual probability generating function for uniform, binomial, geometric, and lastly Poisson distribution. Right, so stay tuned. All right, now next we're going to look at some standard discrete probability distribution function, and then after that we are going to generate the probability generating function for each one of these discrete probability distribution, such as uniform distribution, binomial distribution, geometric distribution, and then lastly we're going to work out the Poisson distribution. All right, now first thing first, let's take a look at the uniform distribution. All right, let x be the discrete random variable that denotes the score when a fair die is drawn. So we need to find the probability generating functions for x here. Now, based on the result from the table here, um, we have the discrete value x ranging from 1 to 6. Okay. Now, each one of these discrete random variable corresponds to its probability, but anyway, all the individual probability is a constant because this is a uniform distribution, right? Therefore, we can denote these distributions as x is uniformly distributed with a constant probability as 1 over 6 here. Okay, whereby the constant is 1 over 6. Okay, now we are supposed to generate the probability generating functions PGF for the x. Right, now the first step would be we're going to write down the functions as in terms of t. So that will be 1 6 t to the power 1 here because the discrete random variable start with 1, and then we have 1 6 t to the power 2 representing the second discrete random variable. Then we have the third one, fourth, fifth, and then lastly we have the sixth. Okay, now from here we can manipulate this function algebraically. So take for instance, we're going to factorize this as T2. Sorry, this is T2, not T3. So T3 here, T4, and then lastly we have T5. In general, there are 6 terms here. You will recognize that very clearly this is a geometric series with the first term as A and then the common ratio as a T here. Therefore, we can evaluate the summation of this geometric series as. Okay, now maybe as a remark, I'm going to write down the formula for summation of geometric series. Now that is given by Sn equal to A 1 minus Rn divided by 1 minus R, where the R is the common ratio. In our case, the R is a T, and then whereby A is our first term, which is 1. Alright, so from here we have 1 minus T to the power of N. We have 6 term here, so the N is 6 in this case, over 1 minus T here. Alright, and then there you have it. This one will be our probability generating function that represent a uniform distributions with a constant probability of 1 over 6. Okay, now, right, as a precaution, before we proceed on to the next example, it's always a good technique to apply here to check whether we have obtained the probability generating functions correctly. So one way to check is by using one of the property of probability distribution. Here we're going to work out our G1 by using t equal to 1, or by inputting the value for t equal to 1 into our probability generating function. So we have 6 1 here. Okay, now this one will be 1 minus 1 to about 6. This is 1 minus 1 here. Okay, now that would actually be 1 6 0 divided by 0 here. Okay, that would be undefined. All right. Alright, so what has happened here? We are not able to um, obtain the expected value of 1 because all probability distributions should have a sum of probability equal to 1 here. So what is going on now? Right? We're going to go through what we have done here and then recognize if there's any small detail that we miss out here. Okay. Now, first of all, for this sum of geometric series, there's a restrictions on the common ratio that we need to pay attention to. If you recall, the restrictions state that the magnitude of the common ratio must be less than 1 here. So that's the reason why in this case we can't actually substitute 1 directly. And then by the way, our common ratio is a t. So therefore the restrictions state that the magnitude of t must be less than 1. Now therefore, in order to fix this, okay, we're going to come back to the drawing board here. Okay, let me erase off this. Okay, now we're going to use this result here. Okay, now uh, that's the reason why it's best to always check whether your probability generating function has been described fully. Is there any detail that you left out? Right? So therefore, because this function here is not completely defined for any value equal to for any value t equal to 1 here. So therefore we have to readjust this form here. Now we can simplify this further as 1 6t. Okay, now that can be written as t3 2 here. Oops, hold on, let me correct that. That should be 1 minus, you can actually use t square 3 like this over 1 minus t. So from here we're going to make use of the algebraic identity of a cube minus b cube identity, which can be written as a minus b a square plus ab plus b square here. Alright, so we can do that here, and then that would be 1 6t, and then that will be 1 minus t square. Okay, so 1 minus t square, is that correct? Yeah, 1 minus t square, and then 1 plus t square, and then plus t4 over 1 minus t here. Now we notice that there's a common factor between 1 minus t square and 1 minus t here. Now we can actually reduce this because the magnitude of t is less than 1. It's not equal to 1. Therefore, we can simplify this as 1 plus t, 1 plus t square plus t4. Alright, now that will be a well-defined probability generating functions for our uniform distributions here. Now we're going to check that one more time by substitute the t equal to 1 again. Now there will be a 2, that will be a 3 here. And then voila, we can see that G1 should yield a 1, which means the sum of probability that we expect to get should be a 1 as expected for all value of x here. All right, and then that concludes our discussions for uniform distribution. All right. Right, next let's take a look at the second example, binomial distribution. Now in this example, it is stated that Wei is a keen archer. He has taken part in many competitions. When aiming for the center of the target, called the goal, he finds that he hits the goal 70% of the time. Now we need to find the probability generating function for x, where the x is a discrete random variable representing the number of goal hits in 4 consecutive shots at the target there. Right. Now, just by reading this sentence here, we know that in both success and failure. So 70% of the time, he's successful in targeting the goal, and then 30% fail to do so. And then the number of trials involved is 4 consecutive trials, and then we are assuming that all the events are independent. Therefore, we can represent this as a binomial distribution. So since x represents number of goal hits in 4 consecutive shots, therefore we will write this as x is any binomial distribution that has number of trials as a 4 in this case, and then our probability of success is 0.7. Right. So where the p usually used to denote a probability of success, 70%, and then whereby the q itself is a probability of failure, in this case is 30%. Right. So I hope that's clear. Okay, and then furthermore, the probability of each individual is can be written as such. Right, so can be written as such, equal to equal to this. Okay, let me write it down here. Now that would be equal to, like in this case is a 4, so I'll just write down as a 4. Okay, so this is given by 4x here, and then multiply by probability of success, and then probability of failure here. Now that will be 4 minus x. Okay, now where the x will be the discrete random variable, okay, whether he's able to make the shot um, 1 time, 2 times, 3 times, or and so on and so forth, right? Or it could be a zero hits. So the x usually start from 0, 1, 2, 3, and up to 4 there, right? So I hope that is clear. Now, in terms of representing each individual component of the probability, we can build the probability distributions table. So let me show you how the probability distribution table actually look like. All right, so you can see that it's over here. Where is it? It's going to take some time to load. Let me get it down here. Okay, it takes awful long time to load the table. All right, now there you have it. So this is the probability distributions table that represent the binomial distribution in our context here. So the discrete random variable range from 0 until 4 there, and then each individual probability can be written as such. Okay. Now therefore the probability generating function we can write as gt in this case. Now can be written as 0. Okay, so maybe I can use the summation notation first before I go into the detail. Now that can be written as the sum of all this. Okay, so the p is 0.7, so I might as well write down 0.7x. This is 0.3 of 4 minus x. Okay, and then we need to multiply by tx here, and then we need to sum up all these individual probability from x equal to 0 until 4. Okay, now that's how the notations look like. Now in its detailed form, it looks something like this: to the power of 4 plus 4 times 0.7 by 0.33, and then time the t plus 6 0.7 2 2 here, t to the power 2, and then after that we have 4 0.3 t to the power 3, and then lastly we have 0.7 or 4 t to the power 4. Okay, so I hope that is clear. All right. Now from here, I'm going to make a remark on how we can actually simplify these long versions of polynomial uh, functions into a shorter version. So the recap of the remark over here. Now we are going to use the binomial expansions formula, which is given by a plus b to the power n. Now a plus b to the power n can be written as here a to the power n plus n1 here, a to the power of n minus 1 b, and so on and so forth until we have n, the last term, b to the power n. Right. Now you will notice that this form looks very similar to these binomial expansions, where the a in this case is the same as 0.3, okay? And then whereby the b is actually 0.7t here. You can actually join 0.7 with the t, so there's 0.7t raised to the power 4, which is our n. So therefore, at this point, we can actually describe the whole summations of this polynomial expression in this form. So there will be a 0.3 plus 0.7 t raised to the power of 4 in this case, because this is raised to the power n, or n in this case is a 4. Alright, now that is how the probability generating functions for binomial distributions actually look like. Now, of course, in general, you have to test whether we have built the functions correctly. So we're going to check by substitute t equal to 1 into our probability generating function. So therefore, in this case, we have 0.7 to the power 4. That will yield 1. So therefore, this is a good check that we have built the probability generating functions correctly. Right. Now, the general probability generating functions for binomial distributions can be written in a more general form. Now, since 0.3 is the probability of failure, so in this case, we can actually write q plus this is a probability of success. So that is a p with the additions of a t here, and then raised to the power of n, depending on the number of trials involved. Right. So there you have it. We have successfully built the probability generating function for binomial distribution. Alright, now next we're going to look at geometric distribution. Now our objective is still the same. We're going to create the probability generating functions that represent a geometric distribution here. Right? Let's read it through. Now a pack of playing cards containing 52 cards with 13 cards of each of 4 suits. Those suits hearts, spades, diamonds, and clubs. Now, a heart is selected at random from a normal pack of cards. Now, if it is a heart, the experiment ends. Otherwise, it is replaced. The pack is shuffled again, and another card is selected. All right. Now, let X represent the number of cards selected up to and including the first heart. So we need to find the probability generating functions that represent the discrete random variable X here. Now we know that X represent number of cards selected up to and including the first heart there, right? Okay, now first of all, you should recognize that this is a geometric distributions because it involves a number of uh, failures before the first success is been achieved, right? So this is a geometric distribution, so we'll write down that as geometric distributions. Now, geometric distributions will have one parameter, which is the probability of success here, P. And then we know that probability of success refer to the chances of getting a heart. Right. So getting one card that shows a heart. So we have 13 cards that represent hearts, and then out of the 52 there. So the uh, s- chances of getting a heart is 13 out of 52, which is actually 1 over 4 there. Right? Okay, so I hope that is clear. Now, for any geometric distribution, it has probability mass functions. So I would say that this is a probability mass functions that is represented by px equal to this. Now it is represented as 1 minus p here. So number of failures before we successfully secure a heart. So that will be x minus 1 here, and then multiply by the p there, whereby the x could range from starting from 1, it could be 2, it could be 3, and so on. Right. Now, this represent number of trials before a heart is being obtained. So it could be uh, just one trial, you successfully secure a heart, or you fail one time and then obtain a heart, and so on and so forth. Now, therefore, you can calculate its individual probability for all these discrete random variables x. Take for instance, if you are interested to find out what is the chances of getting the heart straight away through first selection, right? So that would be 1 minus 1 over 4 here. Okay, so since the x is 1, so therefore there will be a p here. There will be a 0, sorry. And then you can see that from here, we uh, add up to 1 over 4. Or you could calculate px equal to 2, for instance. That will be 1 minus 4 here, 2 minus 1, 1 over 4. Okay, so from here you will get 3 over 4 to the power of 1, 1 over 4. And so on and so forth. You can continue to calculate the rest. Now, all this result, of course, you can organize it in the form of table as such, right? So let me show it to you. Okay, so you can represent all these calculations of its individual probability in the form of table. Right, so here you can see that successfully obtain a heart through first trial. This one successfully attempted 2 times before a heart is being secure, and so on and so forth, right? Now, how are we going to create the probability generating functions using the table, for instance? Okay, now using the table, the probability generating functions could be written as, so let's assume that GT is our probability generating functions. Therefore, the way to create the generating functions from the table itself would be all you need to do is copy its individual probability, and then t raised to the power of the discrete random variable here. So there's a 1. And then after that, you will go on to 1, 4, 3, 4, t to the power 2, and then 1, 4 by 3, 4, 2 t to the power of 3, and then 1 4 by 3 4, right? 1 4 multiplied by 3 4 here, right? To the power of 4 here, and then t to the power of let me see, what do we have here? This is 2. This is, oops, sorry, there. Supposed to be a 3 here. Okay, so there's a raised to the power of 3, t to the power of 4, and 1 4 multiplied by, hold on, 1 4 multiplied by 3 4, raised to the power of 4, t to the power of 5 there. Right, and then there you have it. This is our probability generating functions that is extracted from the frequency table itself. Okay, now from here, now of course it is an infinite series here, so we can actually simplify this summation series. Okay, now you notice that we can actually simplify this, that we can have so let me see what we have here. We have this, and then after that we'll have 3 4 t 3 4 t square, and then we have 3 4 t cube, and then we have 3 4 t 4 there, and so on and so forth. All right. And then you will notice that this is yet another geometric series, so we could actually produce a simplified version of this summation series. That could be 1 4t here, and then it has a common factor of 3 over 4 here, and then that would be 1 minus, okay, I forgot that. Right, now even though this is a summation series, but it is an infinite geometric series, so therefore we're going to use the infinite summations or geometric series that will give us a divided by 1 minus r. So our a is 1 here, 1 minus 3 over 4 t there. And then of course we can simplify that as t over, in this case we have 4 minus 3t here. Okay, now given that, of course maybe we can make a remark here, given that the t should not be equal to 4 over 3. It could be any real numbers except equal to this. So let me write a better remark here. So the t would be all real numbers except equal to 4 over 3 here, right? Or in general, for this particular summation here, based on the geometric summations requirement, the t is supposed to be less than or equal to 1 here. So the more appropriate conditions for this would be this. Right. I could have written down this as this should be less than 4 over 3 here for this summation series to be true, right? And then there you have it. That's how we create the probability generating functions for geometric distributions here, right? Now that is based on the very specific value of probability of success. Now how are we going to create general equations for probability generating functions that represent geometric distributions? So we're going to create a general functions here. So general formula. All right. Now to do that, the same thing. We're going to write down GT here. Okay. And then that will be uh, using the definitions of the generating functions. We know that the probability of generating a function is actually given by, right, this by definitions. So therefore we have it equal to Tx, probability equal to x here, right? Okay, for all x in this case. Now that will be the same as Tx, probability of this geometric distribution is given by this. So therefore, I can actually write it down as now. If you like to represent 1 minus p as q, by all means. So if our q, in this case, I write down as a remark here. So q is actually 3 over 4, which is 1 minus p. Okay, so I try to make a remark here. Q is actually 1 minus p, and then this is a geometric distribution of general probability of success equal to p. Alright, so from here we can write it down as qx minus 1p here. So there's the summations starting from 1, for instance, starting from 1, okay, until infinity. Okay, 1 until infinity here, right? Now you notice that both the p and q are constant, so we can actually take the p over q out. So therefore we have tx qx here. Okay, you will notice that this is how it look like, and then this one further can be described as p over q, qt to the power x, the sum of it. And then you will notice that since our x start from 1 there, so this is actually a geometric series. So therefore we can actually apply our geometric series equations, which is the same as p over q, um, 1 minus qt. Our a, okay, this is our a actually. Hold on, just let me simplify that. Okay, so this one is actually qt, or 1 minus qt raised to the power of okay, take for instance we start from x equal to 1 until n, so that will be raised to the power n, and then over 1 minus qt there, right? Okay, that's how it look like, right? Okay, I'm going to erase these sections here so that we can further refer to this. So I'm going to remove these sections here. Okay. Okay. Now next, from here we can further simplify this. Take for instance, this q can be simplified, and then it will just be pt. It will just be pt, right? Now, for these probability generating functions, we are dealing with, okay, the n approaching infinity. So this is the same as the limits as n approach infinity here for this p q qt 1 minus qt to the power n divided by 1 minus qt here. All right. Now from here, since the qt, bear in mind for this geometric series, the qt must be less than 1. So therefore, these sections will approach 0. And then therefore, by applying these limits, we will end up with pt over 1 minus qt. Right. Now, that will be the general formula for any types of geometric distributions with a probability of success equal to p, and then q equal to the probability of failure here, right? Okay, now I hope that is clear how we create probability generating functions that represent geometric distribution, right? Now next we're going to move on. Okay, now our next distribution is the Poisson distributions. Now, before we go through any discussions regarding these Poisson distributions, okay, I have specifically quote an example just to recap on how Poisson distributions actually look like in this case, right? Okay, now let's read through the questions here. Suppose that there is a disease, all right, now, for instance, COVID-19, for instance, okay, whose average incident is 2 per million people, which means the in infectious rate in this case, or infection rate, is 2 out of 1 million people population, right? Now, what is the probability that a city of 1 million people has at least twice the average incident here? Okay. Now, first of all, we're going to represent our x. X represent the number of incident. Okay. Number of incidents um, due to disease. Okay, I just make it simple here. So number of incidents occur due to a certain disease, for instance, COVID-19 here, right? And then this is Poisson distributions. Okay, so all Poisson distributions can be represented using these notations here. Now it has a lambda, which represent the average incident per million people in this case. So whereby the lambda given here is 2 incident per 1 million people. So this is 2 incident per 1 million people. Right? So maybe I can write down here just as a reminder, 2 incidences per 1 million people. All right. Now the probability mass functions that represent Poisson distribution is given by, so probability mass functions that represent Poisson here is given by this. That is E negative lambda x 0. So whereby the x could be ranging from 0, 1, 2, and so on and so forth. It could mean there's no infection at all, or it could be one infection, so it could be two infections, and so on and so forth. So therefore, if you are interested to calculate its probability in this case, so what is the probability that a city of 1 million people has at least twice the average incident? So twice as many incident. Okay, so at least twice the average incident. So what that mean is, it means that at least is the smallest, at least two two times the average incident, twice the average incident. So twice the average incident is 2, so twice the average incident will be this, will be 4 then, which is the same as x greater than 4 here. Sorry, done. So that is greater than 4, right? Now, how do we actually calculate this? Of course, the usual way would be you can actually get uh, x equal to 4, 5, 6, and so on and so forth, and so on and so forth. Yep, right. Now, of course, doing so is very tedious because this is an infinite summation series. So the other easier way to actually obtain a more finite calculations, right, is by using these methods here. So we could have written this probability as this. So it will be easier to calculate in this case. It will be x equal to 0 and x equal to 3. Okay, and then there you have it. Calculating each one of these probabilities shouldn't be a problem. So just to recap here, it will be E, since our lambda is 2, so I'll write down a 2 here. So 2 to the power of 0, 0 factorial, and then you will continue on with this 1, 1 factorial, 2 to the power 2, 2 factorial, And then, of course, finally, you should be able to obtain an answer for this one here, right? So let me roughly calculate this so that we can verify the answer at least. Okay, so now for these calculations here, the first one is just e raised to the power of -2, and then after that I'll have 2 times e to the power of -2, and then after that I will have like also 2 times e to the power of -2, and then finally I will have like what do I have here? There is a 8, 4, 4, 4 over 3. Okay, so that should be 4 over 3. Let me see here. Yeah, 4 over 3 by e to the power of -2 there. So in general, if I were to leave my answer right now for um, accuracy wise, for instance, I might want to raise it to a larger significant level here. So therefore, in this case, I can conclude my answer as uh, 1 minus 0.8571, which is the same as 0.1429, okay, or approximately 14.3 percent. So 14.3% of the time, we will have at least twice the average incidence occur in these populations here, right? Now, I hope that will give you a good recap on how to apply Poisson distributions. Of course, our intentions for this section is still the same. We are interested to produce the probability generating functions that represent Poisson distributions. Right. Now, I'm going to do it algebraically. Okay, let's take a look at how does it look like. All right, so we are still using the same probability mass functions that represent Poisson distributions here. All right, now we are going to obtain a general formula for the probability generating functions that represent Poisson distribution. Okay, let's look at how does it look like. So probability generating functions GT is actually given by definitions, for instance, is given by Tx here, okay, which is the same as this. Okay, now in general, this is also the same as this one here. Tx, the probability is given by this. Therefore, I can actually write down as x over x factorial. All right, now the x would start from 0 until infinity, of course, right? Okay, now from here we can recognize a few sort of important constant. Okay, so let us see what we have here. So from here, we can actually take out the exponential negative lambda because it's a constant itself. And then after that, we can rewrite this as the t and the lambda can join together. So we have t lambda t in this case, lambda t to the power of x, x factorial equal to 0, infinity here. Okay, now this is exactly the same as this, e negative lambda, right? So when it's 0 is a 1, so when it's 1 is pi t over 1, and then you have lambda 2 over 2 factorial, lambda t 3 over 3 factorial, and so on and so forth, right? All right, now if you recall this as a remark, I'm going to write down at the side here. Okay, as a remark, any exponential or transcendental functions exponential form can be written as 1 plus x squared over 2 factorial, x3 over 3 factorial, and so on and so forth. Okay, now this can be derived from the Taylor Maclaurin series. So Taylor-Maclaurin series. So if you use the Taylor-Maclaurin series, you should be able to show that exponential can be given by this summation series. And then if you compare this summation series with this, they look quite similar. So the only difference is this is x, this is lambda t. Therefore, from here, I can simplify this summation series as lambda t. And then by simplifying this, I will be able to get t minus 1. Okay, and then there you have it. This is the general formula for probability generating functions that represent Poisson distributions with the average value per certain unit quantity lambda. All right, so I hope that is clear for Poisson distribution. Right. Now next we're going to move on to the next section shortly. Right. Right. Now next I'm going to show you how we are going to use the probability generating functions to link these probability generating functions with the expected value and variance for this discrete random variable. Right? Is there any relationship between the probability generating functions that we can extract that is related to the expected value and the variance system? Right? Now let's get going on this. Now, before that, we're going to recap on the definitions for expected value. Expected value, or in general, is the mean itself. So, expected value, or sometimes you call that mean. It can be given by this simple notation here, and then, or it could be written in this notation. Okay. Now, the original definition is given by this. We are talking about a discrete random variable here. So the notations that represent expected value or mean is given as such, whereby the x are all the discrete random variable, right? Okay, I hope that is clear. Now, secondly, we also have the variance. Okay, variance is given by this symbol here, and then variance, the original um, definitions for variance is actually equal to this one here. Okay, now that is actually the definitions for variance, and then of course that can be simplified further into this. Okay, now let me see whether I can work out the original formula that we will obtain in a while. So from here, we can actually expand this out. So therefore, we have what do we have here? We have x squared minus 2 mu x here, and then plus a mu square. Okay, so that's what we have. And then from here itself, we can apply some of the property of the expected value. So that will be the same as ex squared here. And then minus of 2 mu ex, because the mu itself is a constant, plus the expected value for a mu. Expected value for mu is just simply a mu there. And then from here, we have x squared here. And then this can be written as 2e x squared here, because knowing that the mean is equal to this. Okay. And then this one also we can rewrite like this. And then therefore, we end up with this. Okay, this can be simplified into this. All right, and then there you have it. This is the second formula of variance derived from its original definitions here. Right. So we're going to make use of this equation, and then these definitions also, these two definitions, to work out a relationship between the probability generating functions and the mean and the variance itself, right? Okay, now let's take a look how or what is the relationship here, right? Now we're going to start off by revisiting the generating functions, probability generating functions for discrete random variable, which is given by ETX by definition. That is by definition in this case, right? Okay, now it is given by XPX here. All right, so that is by definition. Okay, now from here, we can try to perform derivative in this case, or differentiation with respect to t. So I'm going to differentiate this probability generating function with respect to t. Okay, so we're going to differentiate this. That will be the same as dt, because we are differentiating this with respect to the t. So it would actually look something like this. Okay, we can even further elaborate this by performing the differentiation in such a way. All right. Okay, now from here, the main result that we can obtain will be x. Okay, now this is differentiation with respect to t, so therefore it will be x over t plus x here. All right, so I hope that is clear at this point here. All right. Now you can see that this format here is the same as EXTX expected format. So this is the expected value format, which is exactly the same through the definitions and through both of the definitions of 1 and 2. You can see that EX is a summation of X with P. So if EXTX, right, that must be expected value of XTX there. Right. I hope that's clear. Now, what is more important here would be if we let, so take for instance, if I let t equal to 1, if I substitute t equal to 1 here into my first derivative of the probability generating functions, okay, let's see what we have. So if you substitute x equal to, sorry, if you substitute t equal to 1 here, so therefore we will end up with ex, and then voila, that is the first relationship between the probability generating functions with the expected value. So we know that the first derivative of the probability generating functions with the value of t equal to 1 must be the same as the expected value of x. All right, now that is a very significant result that we have obtained here. Right, so I hope that is clear at this point. Now next, I'm going to show you the next relationship. So the next relationship require the second derivative. So here, this is the first derivative. Now I'm going to perform the second derivative now with respect to t. So if I were to differentiate this one more time with respect to t, I would be able to obtain, okay, I'm not going to write the formal formality anymore, the formal notations. So therefore, if I were to differentiate this one more time with respect to t, bear in mind. So therefore, that will be, hold on, that would be minus 1. Okay, I just noticed there's an error in my differentiations there. Hold on, before I continue, just let me correct that. Okay. How careless I am here. But it's a good thing we pick up the error here. So there's a minus 1. Okay, so I miss out the minus 1 there. So please be very mindful with your differentiation, especially there's a reminder for myself also. So when you differentiate this, if t is the variable that you are differentiating, so we bring down the power here. We have to reduce the power by 1. Okay, this is the part that I've forgotten. But anyway, by letting t equal to 1, we will still yield the same expected value here, right? Okay, now that has been corrected, luckily. Now we're going to continue on with our second derivative. So the same thing, the second derivative will give us um, x minus 1 now, if you differentiate one more time, and then therefore it'll be t over 2 px equal to x here. And then this can be written in the expected format, which is x minus 1 t x minus 2 here. All right. Now again, we are going to substitute t equal to 1 again. So we'll let t equal to 1, substitute t equal to 1 into my second derivative. Okay, that will yield x minus 1. All right, which is not something very significant to work with. But then again, if you restructure that, you will notice that we have this one here. Can be written as such. And then if you rearrange again, we will be able to obtain another relationship between the ex squared and the first derivative. Sorry, the second derivative here. Plus ex. Okay, now that will be a very important result to use next. Okay, why? Because our intentions now is to obtain the variance. Is there any relationship between the variance and the first and second derivative of the probability generating function? So just to recap, I'm going to highlight that one more time. You can see that we have our first derivative, which is equal to ex. So we can substitute this one here into this section. Okay, whereby the second section ex squared can be, we have already obtained the relation here. Ex squared is actually given by this. All right. Now, therefore, okay, I'm going to erase this section here so that we can see the final result here. Okay. All right. Now I'm going to erase this final result here. All right. Now from here, from equations number 3 and lastly equations number 4 here, yeah, maybe I'm going to rewrite this result one more time. So what we have is the first derivative here. We have ex, and at the same time we have the second derivative, or not the second derivative. We have the ex squared equal to the second derivative plus ex. All right. So from here, okay, we don't need this anymore. All right, now that's the main result that we are going to use. We're going to substitute all this result into equations number 2 now. So from here, our variance. Okay, so variance for this discrete random variable is given by ex squared, which is given by this second derivative. And of course, we're going to subtract that with this one here. Okay, I'm going to do it step by step. All right, this is how it look like. And then we also notice that the expected value for x is given by the first derivative. Therefore, we can summarize this as the first derivative. And then this is also the first derivative. All right, and then there you have it. The last most important equations that relates the probability generating functions with its variance and with the expected value here. So I'm going to write it down. Here you'll be equations. Maybe I'll follow the sequence here. There will be equations number, just now we have 3. So this one will be 4 and 5. Okay, so the most important equations to remember, or the property of probability generating functions that we're going to use later, would be this one here, and lastly the relationship between the probability generating functions with the variance itself. right? So I hope that is clear at this point. Stay tuned. We're going to apply these two properties in our next example shortly. All right, example number one. We're going to look at how are we going to make use of the properties or property generating functions that we have developed just now. Okay, now just to recap, I'm going to write down the formula at the side here, or the relationship. The first one that we have obtained is this, is the same as EX. Okay, now, or okay, maybe I'll write it down in such a way. I will say that the expected value can be obtained by using the first derivative of probability generating functions by substituting the t equal to 1. Okay, now the second one that we have already obtained is the variance. So the variance is given by the second derivative, also using the value of t equal to 1 plus the first derivative, and then finally we have the first derivative here. Okay, now those are the formula that we have developed. We're going to use it and then verify our result shortly. Okay, now assuming that the x is the discrete random variable that denotes the absolute difference of scores when two fair dice are thrown. Okay, so the difference could be 0, or the difference could be a 1, or the difference could be a 2, could be a 3, or could be a 4, and so on and so forth. All right, now let me draw out the result for you to see how does it actually look like. All right, okay, just for demonstrations purposes, before we actually obtain this, it will always be good to draw a table like this. Okay, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. All right. Okay. Three, four, five, six. All right. Now let's look at how do we actually obtain all these differences. Okay. Whenever you throw a dice, most probably is either you get a 1 here. Okay. Take for instance, this is your first die, and then this one will be your second die. For instance, you could get a 1, 2, 3, 4, 5. Oops, I missed out the last one here. So just let me fill that up. Okay, so you could have a 6, or here you'll be 1, 2, 3, 4, 5, 6 here. Yep. Okay, now let's look at how do we actually develop the difference there. So if you got your first die to be 1, for instance, okay, and then the second die to be 1, now the difference, we are interested to discover or investigate the difference between the value obtained from the die itself. So the difference will be 0, 0, 0, 0, 0, 0 here. You can see that. And then if you obtain your first die to be 2 and your first one to be 1, then the difference will be 1. And then that goes for all this also. And then same go for this. Same go for this. Same go for this. And then finally you have 1 here. Now, of course, the top part would be the same as the bottom sections here. So this is actually 1, 1, 1, 1, 1. You have 2, 2, sorry, 2 here, 2, 2 here. And then you have 3, 3, 3, 4 here, and 5 here. Right. So generally we have like 1, 2, 3, 4, 5, 6, 6 differences that produce 0. And then each probability is 1 over 36. So this is 1 over 36. So there are 6 of them. Therefore, the chances of getting a difference is 1 over 6, which is the same as 3 over 18 here. Right? So I hope that that is clear at this point. That's how we obtain the 3 over 18. Now, if you are interested to investigate getting a difference equal to 1, so you can count here. We have 1, 2, 3, 4, 5. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, that's actually 10 out of 36. So I'm going to write down here 10 out of 36, which is the same as 5 over 18 there, which is the second one. And then you can continue on with getting a difference equal to 2 here. For instance, here you have 1, 2, 3, 4. 1, 2, 3, 4. Okay, 4. There are 8 of them. So that is basically 8 out of 36, or it could be a 4 out of 18. Right. And then you are going to continue on with difference of 3, 4, and 5 there. Right. Now, I hope you are clear how all these results can be extracted from this uh, big table here into the probability distributions table. Right. And then from there onwards, okay, the usual way to calculate or evaluate the mean of this discrete random variable is usually the original way is by using this, right? Okay. All we need to do is, if you recall how we obtained the expected value, this is how we do it last time. So it will be 0 multiplied by 18 here. You have to do this patiently. All right, let's see what we have. 4 by 2, 18. And then lastly, we have 5, 118 there, right? And then that would actually yield like, let me see, third, 13 here. You have 9, 22, 22, 8, 30, 35. So there's actually 35 out of 18 there, right? Okay, so 35 or 18. Right. Now that is the expected value that we can get using the traditional methods without the use of probability generating functions, right? Now, next I'm going to show you how we can obtain the expected value using the property of probability generating functions. All right. Now, before we can do that, now of course we have to produce the probability generating function first. Now the probability generating functions for this will be, okay, I'm going to write down gt here. As usual, there is a 3 over 18, 5 over 18t, 4 over 18t square, 3 over 18t cube, 2 over 18t4, and lastly we have this. Okay, now that will be our probability generating function. Okay, now of course, if you like, you can do a bit of modifications and so on and so forth. But at this point, it's not a requirement for us to simplify it into any form at this point. Now the idea here is how are we going to make use of this property here? Yep, this one, to produce the expected value. So from here, I can generate the expected value of x quite easily by substitute 1 into my functions t. So by putting a 1 here. By putting a 1 here, I will indirectly get 3 over 18, 5 over 18. Oops, I think I made a mistake. So hold on. What I told you was the first derivative, and then I accidentally substitute directly from there, right? So if you substitute directly from there, the answer must be equal to a 1, which will be a bit ridiculous for my answer in this case. Okay, now let me correct my step one more time. So from here, I need to differentiate this one time. Differentiate this one time with respect to t. So I will get a 5, 18 plus 8, 18, and then 9, hold on, 8, 18, t. Okay, I missed out something there. It always remind me of one of my students. Always reminded me of my t that I always left out. So now I can remember that thanks to news. Okay, so 8, and then I have 9 over 18 t square. I have 8 over 18 t cube. And then finally I have 518 t4 there. Right. So therefore, my expected value can be obtained by substitute 1 into my first derivative. So from there, I will get 5 over 18, 8 over 18, 9 over 18, and finally 5 over 18 there. Right. Now let me try to tabulate this. 16, 26, 26, 35. So that is 35 over 18 there. So you can see that both of these answer does tally. All right. Now you have seen how we can actually make use of probability generating functions to obtain the expected value. Now, of course, from our point of view, it may looks a bit tedious to actually work out the expected value by using these probability generating functions. But in terms of computation, it'll be much more easier for machine. Okay, I would say mainly it's not meant for human if you are using the probability generating functions. It's mostly used for machines to perform computations more easily instead of using the traditional methods, right? And then there you have it. We have already found our expected value x there, right? So do check it on your own. If you found that there's any error, do drop a comment, right? Okay. And then next, we're going to work out the variance. Okay, now let me erase all this. We're going to work with variance now. Okay, now we don't need this anymore. We don't need this either. So I'm going to erase this off. Okay, variance. We're going to make use of the second version of this. Now the variance is given by the second derivative. Okay, the second derivative. All right, now I accidentally erase off the probability generating functions, so I will rewrite that one more time here. Now my probability generating function is given by this 3 over 18. Okay, and then next I'm going to we have already differentiated one time just now, so we have already obtained this. Okay, this is our first derivative. Now next we're going to get our second derivative here. It shouldn't be that tough. Just has to be consistent in this case. All right, and then there you have it. Now, once we have obtained this, getting the variance should not be a problem. Now, I'll rewrite the result that we have obtained previously. So for the first derivative, by letting t equal to 1, I managed to obtain 35 over 18. And now all I need to do is try to evaluate my second derivative, and then um, or through the substitutions of t equal to 1 here. Okay, so putting a 1 inside there. Now in this case, let me see, we have 44, 26. Okay, 44, 26, that will be like 70. 44, 26, 70. Okay, 70 over 18 there. Let me see whether I did it correctly. Sometimes I'm a bit careless with my computations. That's 60, 70. Yep. Okay, so there you have it. 70 over 18 here. Right? Now, once you are ready with this value, all you need to do is just substitute into the formula for variance. Now, therefore, variance can also be written using this form here, var. okay, which is given by the first derivative, 17 over 18, and then add up with my first derivative, and then subtract off with the square of my first derivative. Okay, all right. So from here, I will need to use my calculator now. All right, now let me get through this, and then let's see what do we have here. Okay, so we have 70 over 18 join with 30 over 18, and then minus off with 35 over 18. Is it 35 over 18? Yep. So square there. Is that square? Yep. And then there you have it. Is 665324, or in term of decimal, you can actually write it down as okay, if you like, you can actually write it down as 2.0525 there. Okay, or approximately 2.05. All right. Okay, now I hope that is clear. I have shown you how to make use of the property of probability generating functions to obtain, firstly, the expected value. Secondly is the variance itself. Now, some of you may be wondering, how am I going to obtain the standard deviation? That will be very straightforward. In order to obtain the standard deviation, all you need to do is just take the square root of the variance, and then there you have it. There will be your standard deviation. All right, I hope that's clear. I'm going to move on to the second example shortly. All right, let's look at the second example. All right. Now, for an unbiased coins tossed and the number of heads x is noted or recorded. Now, show that the probability generating function x is given by gt equal to 1 over 16, 1 plus t to the power of 4. Now, from this, calculate the mean and the variance there. Right. Now, first of all, you have to recognize that this is binomial distributions because there is probability of success, and they involve a certain number of trials. So the number of trials, we're going to write it down. Number of trials is equal to 4 here, and then probability of success, the chances of successfully obtaining a heads is half in this case. Okay, and then therefore we know that this is binomial distributions, so we can write down that 4 or 1 over 2 there, right? And then the probability mass function for binomial distribution is given by this. Okay, so which is the okay, what's the formula already? So it's n x here. Okay, I shouldn't have written n here because the n has been given as a 4, so I'll write down x4. Now the probability of success raised to the power x, and then 1 minus p raised to the power 4 minus x there, where the x start from 0, 1, 2, 3, and 4 there, right? So I hope that's clear. Now, of course, you can redo the steps that we have done previously to obtain the probability generating function in this case, right? Or if you remember, the probability generating functions for binomial distribution is actually given by this. So I'm going to write it down. Probability generating functions for binomial is actually given by q plus pt raised to the power of n here, if you still remember. Okay, now whereby the q is given by 1 minus p. Okay, right. Now from here, we can plug in all the values that we have obtained here. Now we know that q must also be a half here. So p and q are the same. N is number of trials, which is a 4 here. So if you try to factorize this and so on, so we will get a 1 over 16 here, 1 plus t raised to the power 4. And then hence, it has been shown that the probability generating functions for binomial distribution is actually given by this one here. Right? So I hope that is clear at this point. Okay. Now next we're going to make use of these probability generating functions to obtain the expected value. So first step, we're going to differentiate this first. Okay, so if you're differentiating this, it's actually 4 over 16 there, 1 plus t to the power 3, which is the same as a quarter, 1 plus 3 here. Right. Okay, so from here, our first derivative, having a t equal to 1, is actually a 2 here. So if you substitute t equal to 1 here, you will get a 8 divided by 2 there, right? And there you have it. Now, secondly, we're going to obtain our second derivative. Yeah, okay, maybe I'll write down my second derivative over here. It'll be easier. So my second derivative in this case would be, yeah, I think I write down, where should I write down here? Okay, maybe I'll continue from here then. So my second derivative would be quite easy. I just need to differentiate this one more time. So I get 3 over 4, 1 plus t, get 2 to the power 2 now. All right. And then the same method that I'm going to apply here, I'm going to substitute t equal to 1 into my second derivative. Okay, now that would be a 3 then, because if you put a 1 here, there's a 4, so therefore the second derivative would yield a value of 3. Okay, now we are very much ready to obtain the mean. So therefore the mean can be obtained using the first derivative. Okay, we know that the first derivative is actually equal to 2, and then we are done. Secondly, the variance. Okay, so the variance, I think I write it down over the other side there. So for variance, itself is given by this. Now, just to recap the formula one more time, it is actually given by this. And then at the same time, it's also given by second derivative. Okay, so my second derivative is a 3, my first derivative is a 2, minus of a 2 squared there, right? So therefore, the variance is equal to 1 here. Right. Now I hope that is clear how we obtain the mean and variance from the probability generating functions of binomial distributions. Right. So next I'm going to move on to the next example shortly. All right. Example number 3. We have a box contains 3 red balls and 2 green balls. They are taken out one at a time with replacement. Now let X represent the number of withdrawals until a red ball is chosen. Now that will remind you this is a geometric distributions, failure before obtain the first success in this case, right? Now we are going to recognize the probability of success first. Successfully obtain the red ball. Now we have 3 red ball out of 5 here. So the chances of getting a red ball is 3 out of 5 with replacement in this case, right? And then we know that this is a geometric distribution. X represent the number of withdrawals until a red ball is chosen. So therefore, this is a geometric distributions with the probability of success equal to 3 over 5 here. Okay. I hope that's clear. And then its probability mass function, just to recap, is given by 1 minus p, or in this case I should have just written down as 1 minus p in this case, which is 2 over 5 here. All right, so 1 minus p, x minus 1, and then p here. Right. So the x starting off from 1 a 2, 3, and so on and so forth. So this is an infinite event here. Okay, and then the probability generating functions for these geometric distributions. I hope that you guys still remember. So the generating function, probability generating functions for geometric distribution is given by pt over 1 minus qt. All right. So from here, I'm going to substitute all the value relevance to p and q. So p is 3 over 5 here. Q is 2 over 5. And then by doing a bit of simplification, I will be able to obtain this. All right. So I hope that is clear at this point. Okay. Now, next, what we need to do is to make use of the probability generating functions of geometric distributions to obtain the mean and the variance. Now, as usual, we're going to carry out the first derivative with respect to the t's. Okay. Right. Now, there are many ways to carry out these differentiations here. We could have used a very direct quotient rule. So I'm going to apply the quotient rule directly first. So quotient rule will be something like this. Okay, so that's how the quotient rule actually look like. And then if you try to simplify, we will get 15 phi minus 2t squared there. And then there you have it, right? Now the second way to obtain the differentiations more easily, of course, there's a one step that is not very easy to carry out, which is to not to rationalize, but to obtain its partial fractions for this probability generating function. Because this is an improper fraction, it's always good for us to perform a long polynomial. Just to recap, a long polynomial division in this case. Okay, so take for instance, in this case, I would actually multiply by, let me see, negative 3 over 2. Okay, so if I multiply negative 3 over 2 here, I will get a 3t, and then I will get a 15 over 2 here, and then therefore I will get 15 over 2 here. Now, by doing so, I can rewrite my gt equal to negative 3 over 2 plus 15 over 2, 1 over 5 minus 2t there. Alright, so therefore I can rewrite my probability generating function in its partial fraction this way. So therefore, by differentiating this respect to t, I can cancel off this one here. Differentiating this is quite easy, so therefore is 15 over 2 here, and then I need to take out negative 2, and then of course that will be squared. Okay, so there's a negative 1 here also, sorry. Okay, because this would become 5 minus, okay, maybe I'll write it down like this, it'll be easier for you to see what's going on. Okay, hold on. So gt can be written as 3 over 2 plus 15 over 2, 5 minus 2t to the power of negative 1 here. So therefore, by differentiating this, we will be able to get negative become positive. So therefore, you get 52, negative 1 here. Okay, and then 5, negative 2t, negative 2, and then negative 2 again. So from here, we will be able to get 15 over 5 minus 2t to the power 2, which is exactly the same as this. Right. So that's mainly up to you which method you want to use here. Right. So once we have obtained this, now we can evaluate the value 1 here. Okay, by putting a 1 here, we will get 15 over, that will be a 9, or you can simplify it into this. All right. Now, next, we're going to differentiate this for the second time. All right, now differentiating this for the second time should not be a problem in this case. So that will be, okay, let me see here. We have 30 and then a 2. So that will be a 60 here. 5 minus 2t. All right. So negative 2 and then negative 2, 4, 60. So therefore, this one will increase to 3 then. And then there you have it. There's your second derivative. Okay, just let me check one more time if I got this correctly. Yep, correct, right? Okay, so once we have this, I also need to evaluate the second derivative at t equal to 1. So therefore, I will still end up with 60 over 27 instead. Okay, so maybe I can like divide by 3, I think. Is it 3? 3, 9, yeah, 320, 390. All right. And then finally, my mean. Okay, so the mean can be obtained using the first derivative, okay, which is the same as 5 over 3. We are done. And then for variance, now that will be the second derivative with the first derivative and then the square of the first derivative. Okay, and then that would yield, let me see what we have, 20 over 9 plus is 5 over 3 minus 5 over, 5 over 3. Supposed to be 5 over 3 to the power 3. Sorry, to the power 2. Okay, let me correct that. That's 5 to about 5 over 3 to the power 2. And then finally, of course, we will get a negative, let me see. So negative 5 over 9. Negative 5 over 9. Is it negative 5 over 9? 25. Yeah, correct. Negative 5 over 9. So therefore, that will be 5 over 9. Then your final answer will be 5 over 9. 3, 15, 15, or 10, sorry. 10 over 9. Okay, so the answer will be 10 over 9. Just let me check that very quickly before I summarize that. So there is 20 over 9 plus a 10, 15 over 9 minus 25 over 9 there. So therefore, I have negative 10, 10. Yeah, correct. Alright, so that is the answer for the variance there. Now, I hope that is clear. I'm going to move on to the next example shortly. Right, let's look at the last example before we move on to the next section. All right. Now here you have a discrete random variable x has a probability generating functions given by such is a plus bt plus ct squared, where a, b, c are constants. Now, if the mean given is 1.25 and the variance is 11 over 16, we need to evaluate the value for A, B, and C there. Right now, that sounds like simultaneous solutions problem solving here. Okay, so let's give that a try. Okay, now first of all, we have our probability generating function here. A plus bt plus ct squared here. All right. Knowing that all the random variables are 0 until 2 here. Right. Now we are given the mean. Therefore, we're going to proceed on with our first derivative with respect to t here. That will be a b plus 2ct. Okay. Now, next, let's move on with our second derivative first. Maybe it's easier in this case. I think it's easier if I write it down at the side here. So the second derivative will be 2c only. let me just quickly check through in case I miss out anything. B plus 2ct, and then lastly the second derivative is 2c there, right? Now next, we are given the mean equal to this. Now I'm going to substitute t equal to 1 here. So if I substitute t equal to 1, I will get b plus 2c. And then this is exactly the same as the we are given. So here I'm going to write down, we are given the expected value, which is 5 over 4 then. And then this is given by the first derivative of our probability generating function. Okay, therefore I can write down b plus 2c is actually equal to 5 over 4. Right. Or generally you can write down as 4b plus 8c equal to 5 there. Now that will be my first equation. I can't do much at this point. Okay. Now at the same time, I also need to work out my evaluate the value for second derivative at t equal to 1 also. That is simply just 2c. It has nothing to do with t in this case. Now, I'm also given the variance. So I'm going to use the variance, which is the same as second derivative. Okay, and then this is given by 11 over 16. Okay, now my first derivative is b plus 2c. And then, oops, my first derivative is b plus 2c, yes. My second derivative is 2c, so I should have 2c over here. I should have this one here. And then I need to subtract off. So subtract off with b plus 2c square. So b plus 2c square. Did I get that correct? Where's 1? Yep, correct. So square. Therefore, I will get 11 over 16 there. All right. Okay, so at this point, I will get b plus 4c minus b plus 2c square equal to 11 over 16 there. All right, just let me check for a while in case I miss out something. Okay, just let me check for a while. My second derivative is there, so it's 2c. Okay, so 2c. It is the square of the first derivative. All right, there you have it. Now that will be my second equation. All right. So at this point of time, we have three variables. We should expect to have three sets of simultaneous equations. So therefore, where is the other sets of equations then? Where is the other sets of equations then? So the last sets of equations actually came from the sum of probability. So we know that the sum of probability must be equal to G1 here, and then the sum must be equal to 1. Therefore, if I substitute 1 inside here, I will get A plus B plus C must be equal to a 1 here, right? Okay, so I hope that is clear at this point here, right? Okay. Now, those are all the equations that I have obtained currently. Right. Okay, so there you have it. Right. So we have all these equations set up properly. Now you will see that your equation number 2 at this point looks a bit weird, like there's a quadratic involved, right? Now it is not actually. So I'm going to consider. Okay, hold on. I'm going to consider equations number 2. Now we're going to look at equation number 2 so that to see whether we can further simplify it or not. All right. Now from these sections of the equations, you will notice that there's actually 2c plus the first derivative. The first derivative is actually the mean. The mean is actually given by 5 over 4. So I could have, instead of writing that, I could have written down that as 5 over 4 instead. And then the same go for this. 5 over 4 square equal to 11 over 16. Right. So let me try to simplify this. So therefore, I will have 5 over 4, 25 over 16 there equal to 11 over 16. Right. So that's what we have. I'll have 36 over 16. Hold on. So that will be like 36. Is it 36? Yeah, 36 over 16. Minus off with 20 over 16. So therefore, I would be able to get a 1. Then you will see that your C is basically just half. Okay, once you obtain the C, we could have substitute this one back into number 1 now. Okay, so I'm going to show you that. This one substitute back over here. Okay, so from these equations here, we will notice that either you use this one or use this one, that's fine. Since I'm interested to get B, so I might as well just write B is actually 5 over 4 minus 2C. All right, my C is 1 over 2 here. Therefore, my B will be a quarter there. Of course, lastly, I'm going to consider equations number 3 now. Once I'm done with that, I'm going to substitute that back here. So from here, I will notice that A plus B plus C is equal to 1. Therefore, A must be equal to 1 minus of half minus of a quarter here. Right? So that must be a quarter also. Right? So I hope that is clear at this point. We have already found all the answer for A, B, and C using all the informations that we have. Right? Okay. So I hope that's clear. I'm going to move on to the last sections of the applications of probability generating functions, and then equipped with some illustrations of examples. All right, stay tuned.